Hi everyone, I'm Dr. James Pickering. I'm a lecturer in control engineering at Aston University, located in Birmingham in the United Kingdom. Today I'm going to give you a talk on Control Lab in the Box that has been primarily used to teach control engineering for a future vehicle technologies MSc at the university. So I'm going to give you initial motivation behind the project. Then I'll go into some brief details into Control Lab in the Box, and then I'll finish off then talking about Control Lab in the Box version 2 that I'm currently working on. So where did the motivation for this Control Lab in the Box approach come from? So at Aston University we have an Origo Autopod, which is effectively a four-seater autonomous electric vehicle that we have navigating around our campus. It's used to demonstrate electrification and also autonomy to students. So for example, if we were looking at vehicle control algorithms, it could be DC motor speed control, DC motor temperature control, and things like perception, so obstacle avoidance. At the university on the MSc course, we have these quite large vehicle platforms known as the Rosbot Plus, and they're used as a proxy for the Origo Autopod. You can see there the dimensions, mass, the max speed, max payload, and the approximate cost. The issue comes with using such a platform is how to teach students the control algorithm design behind such a vehicle as the Rosbot Plus. So in terms of the speed control, if you want students to be able to understand the dynamics, design the control systems, how did we go about that? So I was initially given the task to teach this module. I was given about 4, 5, 6 weeks to develop a module using this vehicle platform on the Future Vehicle Technologies MSc at Aston University. What I did was I initially broke down the requirements into different areas. So in terms of the DC motor speed control, and what I did, I used scaled down electronic components and MATLAB and Simulink, Simulink primarily in the auto code generation tools, and also a model-based design approach to initially get some of the control algorithms working. So speed control, DC motor temperature control, and perception, just to name a few. As I wanted to develop kits or tools that were transportable, I purchased a load of the boxes that you can see, and I formed the boxes up with the corresponding electronic components within there. So the primary aim when developing Control Lab in the Box was to bridge the gap between control theory and practice. So our course was very much focused on practice, but the development of the control algorithms can't be done blindly, so hence we used a model-based design approach, so the use of control theory. The skills and the knowledge achieved from Control Lab in the Box needed to be transferable to the Rosbot platform, and this needed to be done in a step-by-step manner, so it was progressive. So the students wouldn't lose interest early on. They would hopefully find the process of learning in terms of the control algorithms, or some of the algorithms early on, enjoyable. In terms of using processes and tools, these need to be industry standard. So for example, the use of MATLAB and Simulink is standard in the automotive industry. And the Control Lab in the Box, it needed to be portable, transportable, and also easy to store. So in terms of looking at the details of Control Lab in the Box, you'll see there's the storage box, the electronics. So you can see there these are all detailed. I'm not going to run through in this presentation all the details behind all the details. The details are available on a GitHub page. So if you just type in Control Lab in the Box on GitHub, you will find this. And also if you go onto MATLAB Exchange, you'll also find it on there. You'll see in terms of rapid prototyping parts, so at the moment it's using a laser cutter, so acrylic parts, and also 3D printed parts. Various nuts and bolts and also tools that are required to assemble the Control Lab in the Box together. in terms of what Control Lab in the box looks like, it's effective. As you can see, it's kind of like a wheel. It's got a fan, it's got an ultrasonic sensor. So you're probably already noticing how some of the key algorithms are going to effectively work on this for obstacle avoidance, temperature control, and also speed control. You can see the Arduino there. There's also a motor driver and also a breadboard. In terms of the labs, there's in total, you can see there are 4 main areas. So you've got introduction. So the introduction lab involves just using LED and doing on-off, so just using digital pin on the Arduino, and also then doing PWM, supportive modulation. In terms of actuation, DC motor on-off, PWM, and also polarity control. Then we move on to measurements. This is where we get a little bit more involved, because then we start looking at things like temperature sensors and also the use of a low pass filter. So the students going from designing the filter in continuous time, then discretizing this, and then embedding it on, well, finally once they're happy in terms of the filter design and simulation, then moving this then embedding it onto the actual Control Lab in the box rig. Ultrasonic sensor, and then DC motor with an encoder. Then we move on to finally then doing DC motor proportional speed control. Okay, realizing introducing a proportional controller. Okay, you can get certain levels of control, or if you're talking about your requirements that the students would have set at the beginning, we can meet the requirements to some degree, but there is a need to introduce further control. So what we then move on to then is a model-based design approach. The students are using linear least squares for parameter estimation of a DC motor. So the students effectively capture a first order transfer function model in simulation. Then from this, then they can design and tune the controller. They should find that they need a proportional integral controller to achieve the reference and the various other requirements that they would have set at the beginning. Then finally, then there's some further safety features due to thermal aspects of temperature control and also obstacle avoidance. Throughout this, as I think I've alluded to, we are using a model-based design approach. So we're always emphasizing in mathematical modeling and also using simulation tools to design the various algorithms, so whether it's the low-pass filter or the PI controller. And we're also using embedded control for all of these different labs. The above knowledge that the students learn from this is then transferable to the Rosbot vehicle platform. In terms of the success, there's quick survey results here. So from 5 questions, you can quickly see, I'm not going to spend too much time on this, but in terms of topics like Laplace transform, transfer functions, their overall, how confident they feel on control theory, the use of MATLAB and Simulink. After these questions were asked before the use of Control Lab in the box and after the use of Control Lab in the box, and overall all questions improved quite significantly there, as you can see. If you wish to know more about the Control Lab in the box approach, I have done a recording with MathWorks that you'll find on their MathWorks channel. So if you type in Lab in a Box approach for teaching control, bridging the gap between theory and practice, put that into the MathWorks YouTube channel and you should find that video. So what this then moves me on to is the final part of this talk. So I am at the moment working on Control Lab in the Box version 2. This is being funded by MathWorks. It effectively involves moving Control Lab in the Box so it's a little bit more user friendly. So it will involve having various teaching workflows. Again, it will be using a model-based design approach and some of the tools around that are offered on MATLAB and Simulink, so the auto code generation, virtual labs, and various aspects, and also develop our own virtual labs. What we want to do is better align the teaching to real-world engineering practice and also industry needs, and really trying to make the Control Lab in the Box approach so it's more accessible, i.e. reducing the number of components, not needing tools to use this. So for example, reducing the need for screws, nuts and bolts, those sort of things, and also trying to reduce in terms of the complexity of the manufacturing, so really just such that it can just be 3D printed. To strengthen the work, I am forming a project advisory group. And you're all welcome to join this. It'd be fantastic to have everyone on board that's interested in control engineering and education. So what's involved is attending free 1-hour online meetings. I would like you to trial the developed workflows and also share feedback on your experience using the workflows. So if you wish to join the project advisory group, the QR code is located there. Alternatively, the web address is also given. So I look forward to hopefully potentially working with all of you on Control Lab in the Box version 2, which promises to be a interesting, exciting project. Thank you. If you have any questions, please feel free to email me. Thank you.